Hello, dear viewers. In this presentation, we are reviewing the machine learning methods for big data analysis with mega-class installations. We would learn how you can see the molecule, why you need slow-motion cameras of 3-kilometer size, why machine learning doesn't always work for spectroscopy and small objects research, and how we can make it work. And we'll talk about how scientists exchange skills and knowledge for applying machine learning. Let's begin with the basics. To see a very small object and be able to look into the space between the atoms, we use Röntgen X-ray spectrum. It enables us, because of this small wavelength, to look between the atoms. Depending on how the material absorbs X-ray, we will be able to say that the material stops the photons in different places and thus decide on the structure. Let's take copper and nickel. They have the square, the atoms in the square structure, but if you look at the spectrum, that the maximums will be displaced compared to one another. X-ray serves as a measuring tape in the atomic world. The space between the atom and copper is bigger than in nickel, and you can say this based on this photo. Each and every material has its own unique spectrum, and based on that you can say a lot about the structure of the material. But an unprepared researcher without a supercomputer will not be able to analyze the experimental data received. So let's think and learn how we analyze these fast processes and then decipher, using machine learning, the results we get. We are used to living in the normal world where people work with the objects of a characteristical size of 1 meter, and the sensitivity time for the person is about 1 second. Very small things move much faster, like milliseconds and microseconds for human cells. And with Fire and other small particles is 1/millionth up to 1/billionth of a second in motion. So we need a photo camera capable of doing millions and billions of shots a second to understand how the molecule works. And it needs to be an X-ray photo camera. The science wants to know how the molecule moves. We need not only to know its structure, but how it changes during chemical reactions. For example, new screens, flexible screens, are created using organic LEDs. Those are the molecules that can change their properties depending on the external conditions. Or in photosynthesis, under the sun, photosynthesis uses active protein centers to work. So if the scientists would know how those proteins work, they will be able to create water and oxygen. New catalyzers require you to know how the reactions happen on, for example, platinum catalyzer. Recording huge amount of information is done currently with an optical impulse with a length of like 1 billionth of a second. To understand the physical limitations of such processes, we need to know how the material structure behaves after being subjected to laser radiation. The experiments that are held by the scientists uses a short laser impulse to affect the molecule and change its state from one to another. And using these spectrums of X-ray reaction, X-ray absorption, we can understand how it behaves in different situations. To measure the molecular spectrum, we have huge things called synchrotrons. It's particle accelerator, but not a hadron collider where you accelerate heavy things like big atoms, but they have electrons instead, and after hitting at something at a turn, they emit the light. Our country has invested 25% into a Hamburg accelerator, 3 kilometers long, underground, and this 3-kilometer long accelerator is used to produce short and bright X-ray bursts. This is, you will have to trust me that this is really a 3-kilometer long accelerator. And in the end, I will give you a link to our lab site that you can use to watch the video. So here's how the experiment looks. You run the reaction with a short laser impulse. It's depicted in orange here. Usually you put the example into water, fast-running water, because of course X-ray destroys the example immediately right after making a photo, so we push some new portion of the exemplary, and after the laser impulse there's an X-ray impulse that makes the photo. And imagine this happens 27,000 times a second, so you get 27,000 photos a second, and try to find something useful in those photos, be able to process something, and you don't have enough time, like 3 or 4 days, because new groups of scientists arrive every 3 or 4 days, and you need to, in real time, to understand what's happening, what are the reactions, and here is where you need machine learning. Unfortunately, it's not that easy. First applications of ML in X-ray spectroscopy have appeared just recently, 2 or 3 years ago, and our group was among the first to apply those methods and create approaches for structural analysis. So let's see what are the blockers here. First of all, we don't have full databases. So we lack tens of thousands of X-ray spectrums for known structures. We cannot provide the algorithm with the complete database to train it. The next issue is the experimental issue. The same material researched in the lab or on a synchrotron, depending on the settings, the spectrum will be a bit different. Like here on the picture in the middle, you see the blue and the red spectrum for cuprum, but it looks differently. So if the machine just gets this spectrum, it sees that there are differences, and it will be hard for it to understand that it's the same material. Of course, you can calculate the theoretical database, but the there are issues there too, because the theory is different from the experiment. The calculation needs very complex computers, and current methods don't give the results that exactly the same that experiments. Current works analyze theoretical data and try to understand what can and cannot be predicted on a theoretical data sets. So here we've used a neural net to analyze the spectrum and classify the surrounding atoms around the central atom, or whether it be and we analyze the main components to ensure improved accuracy of the prediction. In other methods, you take all the points, all the pixels in the picture to predict the form and size of platinum nanoparticles. We apply two different approaches. First is the reverse method, where the whole spectrum is considered to be a function of the structural parameters. To the right you have a molecule with 4 distances, P1, P2, P3 and P4, and each and every dot on the spectrum is a function of those 4 structural parameters. So by defining those parameters we can predict the form of the spectrum and find the ones that will give you the closest to the experiment results. The other approach, a direct method, more classical one, is when with all the points on the graph we predict the parameters, but usually we do it step by step. To create the training data set, we generate the points. Usually we use latent hypercube, IHS, that by using the same amount of dots and of points, the latent hypercube enables us to put the points in a way that the projections on each and every axis will be this roughly covering the axis. We use different methods for improving, and here is how the spectrum set looks like for X-ray absorption, and as an algorithm we have started to work with even before the ML methods gained popularity. We actually used polynomials, and now we usually use radial basis functions. Sometimes we use extra trees or regressions, but mainly the radial basis functions work well for this size of the training dataset. As a direct method, we use a neural net. And let's see what are the limitations here. Let's see it. Let's look at the practical examples with real data. In our recent work, we were researching a molecule that can be used as magnetic switches, and by putting the light on the molecule, you can switch it into different states, and it's like one bit of information. Chemists call it spin crossovers that change the full magnetic momentum to be like 1 or 0. We have researched the X-ray absorption spectrum to understand what is the life cycle of this molecule. So for how long can we use this switch, how long will the information be held intact, and what is the minimal time that this bit will be written. To the left you have the spectrum. The black one is the experimental results, and the red is the theory. So the black one, funny enough, we got it in 100 nanoseconds. We got it. And the red is our theory, so we gathered, we found the parameters with which the theory describes the experiment to the best extent possible. And we also built a heat map of the areas with the structural parameters that are okay for our method. The advantage here is that we can use the same data set in different experiments for analysis. So it can be used directly during the experiment. So say you've come to the object and you are measuring and you have an answer in like 5 minutes because of the inference. So you get the results during the experiment. Here's the reverse method. So we were varying the parameters and predicting the spectrum. And with the direct method, we got some issues. After directly putting the spectrum there, it is hard to expect the high accuracy. And the worst thing here was shown, like you have aurum and two chlorum molecules, and they look the same, right? The one below just switch it 180 degrees and it's the same as right? And if we call mathematically P1 and P2 here and P1 and P2 there, it appears that the same spectrum would get two different sets of structural parameters. So if you don't think about how you choose the parameters to predict and how you train, then you usually get bad results. Our aim is not to create new machine learning approaches. Our aim is to understand how we can use the existing ones with the best efficiency. And here we can add new parameters like radial distribution, not the left and right distance, but instead we say the smallest and the biggest distance. Also, to remove the spread, we may predict probability rather than the value itself. And if it can get both of the parameters, then the function will give us two maximums. So for the same angle, we had pure peak around 10 degrees. And to the right, you have roughly the same probability for a lot of different values of angle. Now let's talk about sharing knowledge. The scientists like to use Jupyter Notebook, and where you just write some code, you publish it, and we share those notebooks with specific tasks already solved. And we share them together with the needed distribution. We have a site also dedicated to our software and our approach that has data sets for different goals. Jupyter Notebooks are very convenient to analyze the quality approximation, compare theory with experiment, and you share basically your whole process for both the scientific thinking and the results. So a new person will be just able to upload his or her own experiment and get the results with the full analysis comments for the experiment. There's a big group of people, the green ones, mathematicians from the Mechanics and Math University of Southern Federal University, The blue ones are the physicists, and our goal is to formulate the tasks, and analyze the data for the practical implementation. So we have also a link to our site. We invite everyone who is interested at machine learning methods, and I will be happy to get your emails and questions on guda@sfedu.ru. Unfortunately, we did not get the video. We did not see the video, but please come to this site, because there we have also a lot of interesting materials. Thanks indeed for your time and attention, and if you have any questions, feel free to tell me.